This is chapter 5, number 23. The setup we have here is a car, distance d up here on the hill, and it's going around in a circle. And it's supposed to stay at this location, this distance d, from the bottom of this like racetrack, if you want to think about like that, this bank turn that just goes around and around and around. It should be able to stay here without needing any support from friction. Okay, so there's not a frictional force here to keep it at that location. All right, so I've already got my picture set up, and in the problem it was given that it's going around at 34 meters per second. And next thing I'm going to do is draw a free body diagram. Since it's going around in a circle, I'm going to call towards the center of the circle positive, so I'll note that here before I forget. So left and up is positive like that. So towards the center of the circle and up. You always want to do that to make sure life easier if you call towards the center of the circle positive. So free body diagram, you got a normal force up and to the left, perpendicular to the surface. We've got force of weight going down. And since there's no friction, that's it. That's all we got. The force of weight will be, of course, mg, or have magnitude mg. And let's see, did they give us the mass? I don't think they gave us the mass. Nope, they didn't give us the mass. And now we got to start solving. So we're going to do a bunch of summation of forces. And since we've got something moving around in a circle, I'm also probably going to want to figure out what the radius of this circle is. I'm going to do that here ahead of time. I'm going to draw a triangle. If this is 40 degrees, and we're going up here to the vertical, this has to add up to 90. So this angle right here will be 50. So there's my D, there's my R, and there's 50 degrees. I'm going to need that because what will probably happen is I'll solve for R because I'm going to be doing stuff with circles, and I'll need to be able to relate it to D. So that is, let's see here, we've got the hypotenuse and the opposite. So opposite and hypotenuse, we've got sine. So sine of 50 degrees equals the opposite over the hypotenuse. And I can now solve for, which one am I trying to find again? I'm trying to find D. I'm looking for D, so I'll solve this for D. So multiply both sides by D, and D will equal R divided by the sine of 50 degrees. I don't know which one of these I'll use, but this is information I'll likely need at some point. Let's start summing our forces now. Let's do this in the x direction, which is the same thing as summing forces along the radius. The x direction is along the radius. So I'm going to write mass times centripetal acceleration. And how many forces do we have? Just one. So it's the normal force in the x direction equals m. And since I was given a v, and I'm going to be doing stuff with r, let's go ahead and put in v squared over r. At this point, it looks like I'm stuck. Okay, I don't know m. I don't know the normal force. I don't know r. All I know is v. So I'm going to keep summing forces. Sum forces in the y direction. And based on how this problem is set up, if it's going around a circle on the track and d is not changing, that means this right here, this displacement in the y is not going to change, which means we're not accelerating at all in the y direction. So I'm going to put 0 here. It's just around in the circle. And in the y direction, we have the y component of the normal force and the weight. So we'll subtract. I'll go ahead and put in, do I want to put in mg? Yeah, let's go ahead and put in mg right now, because I already talked about up here weight mg. So we got normal force minus, normal force in the y minus mg equals 0. And it still looks like we're stuck. So we've got normal force in the x, normal force in the y. But I see some m's here. Maybe I can do some way to relate these two, the x and the y. And you might write something with cosine and sine and theta, or you could relate these with tangent. But I need another triangle here. I need to figure out what that angle is that I got here. So now I'm going to do some geometry here, and hopefully we'll get there. So here's my track. Let's see here. This is 40 degrees. Let's see here. Where do I want to go? This is 50 degrees. And here's the direction of my normal force. So let's just go ahead and extend that line up to here. Okay. And now I think, yep, if this is my track and I draw a perpendicular, this is 90, this is 50, so here I've got a 40. So I got lots of angles to work with now. And let's see if we can get a relationship with normal force there. What do I want to do? So let's draw this. There's normal force, and Let's draw the x and the y. Let's make it look like, let's make the y look like this. So there's the normal force in the y direction. Let's turn this down a little bit. Here's normal force in the, oh, what am I doing? Here's normal force in the x direction, and now we have that angle right there. So let me, just to make this perfectly clear, let me draw a line right here. Okay, here's the normal force going off like that. Here's the y part, here's the x part. That was my attempt right here. Normal force, here's the y, here's the, normal force in the x, here's the y, here's the whole thing. I'll put it on here too. Here's the normal force in the x, normal force in the y, and now I do have a 40 degrees there. And since I'm trying to relate the x to the y, I'm going to do something a little different than you guys have probably done before. I'm going to go ahead and use tangent. And I'm going to write tangent of 40 degrees equals the opposite, which is fnx, over the adjacent, which is fny. It would also be okay here to do the whole f cosine theta, f sine theta thing to eliminate the variable, but this works just as well. Since I'm not looking for the normal force in particular, I'm looking for d. It doesn't really matter how we attack this from the geometry standpoint. So fnx equals fny tan of 40. Fny tan 40. And now let's start putting checks by what we know. We know g. We have a way to relate x and y, so that's good. And we know v. Let's go ahead and do some substitution, see if we can get a little bit closer. So I'm going to put this in for fnx up here, but I'm going to rewrite down here. So let me just draw an arrow. So fny tan 40 equals mv squared over r. And here I have one that says fny equals mg. Fny, lots of subscripts here, equals mg. Section off my work here a little bit before I'm going any further. Keep this stuff straight. So this is from summation forces in the y, fny equals mg. So I get to plug in an mg right here. Hey, that's good. Mg tan 40 equals mv squared over r. And we did have a problem because we didn't know the mass, but long and behold, not surprisingly at this point, the m's do cancel out. We know g and we know v. Hey, we're home free. We can get r, and then we can go back up here and get our d. But I'm going to keep going. So let's figure out what, let's solve this for r. So multiply both sides by r. So I'll get r equals v squared over tan 40. V, if we remember given from the problem, was 34. So 34 meters per second divided by, or that's squared. Don't forget to square. Tan 40 equals something that we'll figure out here. I better check, make sure I'm in degree mode. Yep, I'm in degree mode. So let's take 34 squared and divided by the tangent of 40. We get, whoa, that seems like a lot, but I guess that could be right. 1,377.7. Obviously, I'm not doing sig figs here. Please do not leave comments about sig figs. Okay, a reasonable number of digits, probably just call that 1378 or maybe even 1400. I'm going to leave it like that for now. So we go up here and apply my solving for d because we're trying to find. So d will equal that number, 1377.7. divided by the sine of 50. I'll go ahead and round it off on here. 0.7 divided by sine of 50. And we get 1,798.5 about meters. And I think that's what we're trying to find. Let's see what the keys got here. Chapter 5, number 23. Yeah, something went wrong. Let's see here. I thought that number seemed a little bit big. Probably forgot to, let's see, let me check my units here. 34 meters per second, 40 degrees. Where'd we get that big number from? 34 squared. Squared over r. V squared divided by tan 40. Something less than 1. It should get bigger than 1. Let's see here. 34 meters per second. Let's go back here and see if this is right. D sine 50 opposite. Sine 50 equals the opposite over the hypotenuse. That's right. Check my y direction. That's right. Check my x direction. Only one thing in the x. That's right. Check my tangent here. Double check my angles in here. So if this is 50, yeah, that's 40. So tan 40 equals the opposite, x over the adjacent. That's right. So multiply by both sides. So that's right. Plugging in for fnx, fny tan 40. That looks good. Plugging in for normal force in the y direction. I get to plug in mg, yes. So mg tan 40 equals mv squared over r. That all looks good. So it's got to be something here at the end. The physics is right up till this line at the very least. So m cancels out, and then I multiplied both sides by r. So the r's over here cancel, and I get, oh, there it is. R equals, I lost a g. Right there. I lost a g. I should have divided both sides by g. We lost it right here. It should be on the other side of the equation, divide both sides by g. So I'm going to go down here and put it in. Just g, and then g. And as a result, I'm going to recalculate this number. So I'm going to take my 1377.7, and I'm going to divide it by 9.8. Hey, we get something a little bit more reasonable. So that's the wrong number. So 140.6 meters. Go back up here using this equation for d. Cross out that number. So 140.6 meters divided by sine of 50. Oops. Not the exponential. We don't want that. Sine of 50. Oh, no, that was the exponent button. And we get 183, moving the decimal around basically. We divided by about 10, so 183.5 meters. And now let's see what the book got. A, 184 meters, right there. So it looks like we're okay for D. See if there's anything else we had to solve for. I don't think so. Nope. And this was the car going around a circular path, and then we did not need any friction. If there was friction, friction might help us also go around in a circle, might help us change our direction, but that was the condition. They're saying, let's assume that we don't have any help from friction. What's D have to be for us to go around the circle at 34 meters per second?